Hello everyone, welcome back. What I'm going to do in this video is give you a quick visual explanation of what big O notation means. Now, in the world of computers, big O notation is a way to express how efficient your code is running. It's an estimation of sort of the general worst case of how your code is running. The author of our textbook shows you several different types of functions that we can use in big O notation. I won't go over absolutely all of those in this video, but I will show you the most common ones that we are familiar with to this point. As you can see in this code, I've created two lists. The first one is this one, which is a one-dimensional list. The second one is this. It's a two-dimensional list, 5 rows and 5 columns. What I'm going to do is I'm going to call these three methods that I have defined. One's called display an element. The next one is called display a 1D list. The third one is called display a 2D list. Now, what I'm doing here, before I call the display an element, I'm going to create a variable that will contain the index of the element I want displayed. As you can see, I'm using a random number generator. In order to use this random number generator, first I had to import the random module. And then within the random module, I call this method randint, this one right here. It has two parameters. One, the smallest value you could possibly have out of the random number generator, and the largest one. You may recall that lists in Python can use this len function, which is short for length. That returns the length or number of elements in the list. But as you also may recall, when you use indexes to access an individual element of a list, indexes start at 0. So the first element, in this case the 10, would have index 0, and the last element of the list would always have an index that is equal to the length minus 1. So those are the values I want to randomly generate. And as you can see, here is my display an element function. Just display the index, or the element at the index that is set as a parameter. So if we run this again, here the element at index 5 is 60. 2, 4, 5, right? That is the correct one. Index 1 is 20. Run it again. Index 0 is 10. But the main thing to understand about this is the following. We're not accessing the entire array. Once we get the index we want, we just access that element. We're not searching the entire array to find it. We're like, here's your index. Now go get this element. Since you're really only doing one element out of how many are in the list, this is referred to as being O of 1. Since you're only accessing one element or doing one operation, if you will. Now, in contrast, let's look at the display a 1D list function. We send the 1D list as a parameter, and here it is. So here I'm saying, here is your 1D list. I'm going to print it all on one line. As you can see right here, just a moment. Here's my output for that function. This is the display a 1D list. But what I'm doing here is I'm using a for loop to go through all the elements. As you can see, I have a variable named index, and we're using the range function. We start at 0. We're going to go to the length of the list minus 1. You know what? I think I'm missing an element here, but we can fix that. I actually want to say, the length of the list plus 1. Because if you recall the range function, say the range function was set up to go 0, 5. What would actually happen in the range function is it would go 0, 4. It would not go all the way to 5. Since I want to go, no, it should be the length of the list. This is what it should be. I want this to go from 0 to the length of the list minus 1. Therefore, to be sure I get all the elements of the list, and here I now have, my range function must go from 0 to the length of the list. It will use 0 as an index, but the range function will not use the length. It will use the length minus 1. It will only go up to the length minus 1, but it will not go to the length of the list. And there I get all my elements. The main point, though, is that we used a for loop to access all the elements of the list. We're not just accessing one element like we were in the previous function. We're accessing all the elements in the list. And since we're going through all the elements of the list, whatever the length of the list is, this makes this function O of n. You're like, well, isn't this particular one O of 6 since we have 6 elements? Well, okay, technically it is. But what if our list was 10, had 10 elements? That would be O of 10. What if it had 20 elements? That would be O of 20. So n can represent the length of the list. And since you are having to access all elements of the list to make this work correctly, then this function will be O of n. Finally, here we are calling display a 2D list. And we're setting the number of rows and number of columns. In this case, we have 5 rows and 5 columns. So I think I want to say range from 0 to rows and range from 0 to cols. When I run it, now I get all my elements. But for this one, the X loop, that's the outside loop, goes through all n rows, however many rows you have. The Y loop goes through all n columns. In this case, it's 5 by 5. So we have n times n operations to display all the elements. So that makes this big O of n squared. Suppose it was a 7 by 7. Well, there would be 49 elements to be displayed. They're all here. This one's a 5 by 5. There are 25 elements. They're all displayed. So however many rows, however many columns you have, n times n, if they're both the same, that makes it O of n squared. Now, the reason we use big O notation in programming is to give ourselves and our fellow programmers an idea of how efficient this code is and how much processing time it might take up. O of n squared is usually considered not very efficient. Now, in this case, it really doesn't make a difference because we have a 5 by 5 list. So there's 25 elements. But suppose that got bigger. Suppose you had 10 by 10 or 20 by 20 or 50 by 50. The bigger you make it, the more processing you have to do to display each element. Through some tutorials I took myself, I came across an author who brought up this. It's called the Big O Cheat Sheet. Here you have the most common Big O notations that you run into. Down here at the bottom, you say O of 1 and O of log n. They're at the bottom because they are considered the most efficient. Notice they're in the green. So if you're in green or light green, it's excellent or good. O of 1 is absolutely the best you can get. O of log n, which I don't have an example for, sorry, is the next best you can get. We'll see later when we get into certain linked lists or binary trees that getting the elements out of those is O of log n, which is more efficient than you may realize. O of n is considered a linear function. It's okay, not great, but it's better than some of the other ones. Here we have O of n log n times log n. By the way, when you see log, we're talking about a base 2 logarithm. That's what this usually means. Not base 10, it means base 2. As you can see, that's in the orange, which is bad. N log n is mostly used for searching or sorting. Most searching or sorting algorithms wind up having an efficiency of n log n. We'll talk more about those at the end of the course. Here are the ones you don't want. You don't want O of n squared or O of n cubed or anything with a quadratic. As you can see, the bigger n gets, the more operations you have to do, and that gets very inefficient. This one here is even worse. It's O of 2 to the n. We call that the exponential function. That really, as n gets bigger, this gets even way bigger than n squared. And then this is one I really haven't seen much of myself, O of n factorial, which is apparently the least efficient you can get. Well, as you can see, this chart you're looking at is on a website called this, bigocheatsheet.com. Feel free to look at that. In fact, there's a link to it in the quiz review document for this week. Feel free to take a look at that as you are going through the material in the textbook for efficiency and big O notation, which is in chapter 3 of this week's textbook. Yes, here's the chapter 3 PowerPoints. So it's chapter 3 of the textbook you want to look at for information about big O. If you have any questions, please send me an email at kmuldrow@lbcc.edu.